All right, folks, so in this video, I'm going to do two example problems using conservation of linear momentum. First one comes out of the textbook, and it's problem number 28 here. So I'll give you a chance to read that question, pause, and look at it, write down some information, um, and we'll do that. And then the other one is one that I wrote myself, so we'll do that one next, and you'll see that one afterwards. Feel free to use this video however you like. I'm just going to refocus my camera, and so we can solve this problem. So take a picture of that, pause it, write it down, whatever. Okay, so we have two friends who are going sledding, and it's snowing outside right now, so I would think about going sledding later. And so here's the information. And so the kind of key to starting this problem is understanding that they are going to essentially latch together once they collide. So one friend is running after the other one, and they runs on and hops onto the inner tube, and so they're going to have the same final velocity. So this is going to be a completely inelastic collision. If you wanted to think about kind of why we're able to use conservation of momentum, they represent a closed and isolated system, meaning that when Miranda hops on, she's going to exert a force on Ashley in the inner tube, and Ashley in the inner tube are therefore going to have to exert an equal and opposite force on Miranda. Because Miranda is kind of catching up and colliding with the inner tube, what's going to have to happen is Miranda is going to have to slow down a little bit. And because Miranda is introducing momentum into the system, Ashley's going to have to speed up a little bit. And so their final speed should be somewhere in between 2.7 and 4.5. Now, this problem I would describe as like relatively simple because they're moving in the same direction at all times, and that's going to kind of make things easier. So as far as an inelastic collision goes, they start with separate momenta because they are separate from one another. But once Miranda joins the inner tube, they are now traveling as if they are one big object. And so that's what we're going to focus on. So this is our inelastic collision formula based on the idea that they have a common final velocity. And that's really the only thought I need to give this is once I've identified it as a collision, I can apply conservation of momentum to find their common final velocity. And so 71 kilograms is Ashley's mass. Her initial velocity is positive 2.7 meters per second. So, this textbook problem is nice in that it tells you what direction everything is moving. You're not left to infer. There are some situations where you could infer and others where you really can't. So that's kind of the before scenario. Sorry, this is not fully focused. Hopefully this works. And that's pretty good. And then at the end, they have a combined mass and a common velocity. So it says, ignore any friction effects and ignore the mass of the inner tube. We're just focusing on the mass of the kids here. Their mass is going to be significantly larger than the inner tube because the inner tube is mostly air. So, it's up to you how you solve it. I would say at this point in time, you've done enough math that you can just solve it in your calculator right now. But if you wanted to solve everything first, you could leave it symbolically, divide both sides by the sum of their masses. And so the final velocity would be all of this, which is their total initial momentum, divided by their combined mass. So, if you're interested in putting it in your calculator all at once, I would start some parentheses, 71 times 2.7 plus 58 times 4.5. So that's the total linear momentum. And then we want to divide that by their total mass. Their total mass is 71 plus 58. And we get a final velocity of 3.509. So everything's to 2 sig figs. So the final velocity is going to be positive 3.5 meters per second. So that's it for this problem. And you notice that, hopefully, the final velocity of the two of them is in between their initial velocities. So, something to kind of break apart here is Ashley actually experiences an increase in momentum, Miranda experiences a decrease in momentum. So that's still happening. Even though they end up in the same location, each initial object has to experience a change in momentum, and those changes have to be equal and opposite. One other layer to this is because Ashley's mass is greater than Miranda's mass, Ashley will experience a smaller change in velocity. This is another visit with Newton's second law, that the larger the mass, the smaller the acceleration. But Ashley's velocity goes from 2.7 to 3.5. That's an increase of 0.8. Miranda's velocity goes from 4.5 to 3.5. That's a decrease of 1 meter per second. So the larger mass object will always experience a smaller change in velocity. Next problem I wrote on my own. So you can, pause and take a minute to read this and maybe set it up and try and solve it yourself. But this one I tried to make a little bit more difficult. So feel free to try it on your own and pause, or just watch me go through it. 2 globs of goo. So I chose goo because they're going to stick together, and they're going to stick together in midair. And because things are different between them, they're going to move in a specific direction. The key is that they're thrown at one another. So you have to essentially decide what's happening. I'm going to imagine glob 1 is going this way, and glob 2 is going this way. And when they meet in the middle, they're going to form a glob between the two of them. And the question is, which way and how fast is it going to move? Now, because I drew this diagram, I see that my arrows of where they're moving are different. And so I'm going to imagine that glob of goo number 1 is moving in the positive direction, and glob of goo number 2 is moving in the negative direction. And that's very important because velocity is a vector, and we're dealing with a conservation of something that is a vector. The direction is critical. And so it's important that you realize that there are no negative numbers written in the problem, but in order to be thrown at one another, one of them has to be moving in the negative direction. Again, they're going to stick together. So I am going to write my equation for an inelastic collision. So I apologize, these problems are very redundant because they're both inelastic collisions. But I hope to show you the difference between the previous problem and this one. Okay, so glob of goo number 1 has a mass of 0.75 kilograms and a velocity of 5.5 meters per second. Glob of goo number 1 was moving in the positive direction, so you don't have to write it in, but I'm going to put a positive next to 5.5. Obviously, I'm writing this equation wrong. For glob of goo number 2, it has a mass of 0.65 kilograms, and it's moving at 5 meters per second, but it's moving to the left. So it is moving negative 5 meters per second. So it's moving in the opposite direction. What is their final velocity if they stick together? So they will have a combined mass, 0.75 kilograms plus 0.65 kilograms, and a common final velocity. So, you saw some energy equations get fairly lengthy, and these kind of get bulky too. So again, the math is basically the same, but the important difference here is that you always have to infer the direction of the velocity if it's not told to you. So much like the last calculation, I can plug this all into my calculator. So the numerator of my calculation is going to be 0.75 times 5.5 plus 0.65 times negative 5.0. So that's kind of the important thing there. And then I'm going to divide that by their combined mass, 0.75 plus 0.65. And I get 0.625. And the important thing to recognize is I got a positive number. So positive 0.625, so I'll round that to 0.63 meters per second. And so this means that the pile of goo, once it sticks together, it is now moving to the right. much slower than either one that started, but is now moving to the right a little bit. And basically that's because the momentum of glob number 1 is greater than that of glob number 2, right? It has a bigger mass and a larger speed. So it's bringing more momentum to the system. And so its momentum dominates and ends up the entire thing having momentum to the right. So there are two example problems. We'll go through more in class for sure because there's lots of little, tricks and types of interactions that we want to focus on, but those are two problems to get you started. Thanks.